Welcome to this short video in which I'll try to explain the workflow in order to get the most accurate measurements with cycling 3DMA, in particular when we use this application to measure bikes. This will also help me to explain the different sources of error which can happen or can appear in the system, in the measurements, if we don't take care of a few little things. Not difficult to explain. So I'll follow these points in here, 0, 1, 2 and 3. Two of them have to do with the preparation of the system, basically during the installation or the periodical check, which is done, I don't know, maybe usually once a week or once a month, something like this. And the second and third and fourth points should be considered whenever you start a new recording with a bike. As you will see, I'm using a few numbers on the right, which can be red or orange. These red numbers show the potential error that can be added to the system, to the measurements, if this item in particular is not taken into account or well considered. The red ones will affect the entire calibration or the entire recording quality, and the orange ones will affect only certain measurements in the bike, only a few measurements, specifically in bike measuring. So let's get started. The first aspect that you should always take into account is the calibration, how well you calibrate the system. Calibrating the system well is not that difficult. You just need to bear in mind 2 or 3 aspects. The first one is you need to make sure that the calibration rod is properly mounted. More specifically, you need to be sure that the distance between segments is 300 millimeters. And as an overall checkup, you need to make sure that the distance from 1 to 7 is 180 centimeters, which is the sum of all of them, obviously. So what happens if we move one of these markers maybe a few millimeters away, like marker 4? If you push it up, then you'll have a shorter distance between 4 and 5 and a longer distance between 3 and 4. Now these 5 millimeters don't seem too much, but what are the consequences? Well, basically that the system is using the distances which are known to it. It is using these distances to calibrate the motion of the markers in this region. So if a marker is traveling later on from this point over here to this point over here, intuitively you can think that the marker is traveling, physically speaking, 295 millimeters, but the system will expect that it is traveling 300 millimeters because the system assumed that the distance between 4 and 5 was 300 millimeters. In other words, if the error is significant in the positioning of these markers, like 3, 4, 5 or more millimeters, the system may allow you to calibrate, but the calibration in those regions will be not as good. So that's one thing that we need to do. Later on we'll see how to do this in a practical way, in a very simple way. Obviously once the rod is mounted, once the rod is prepared, that's it. You don't need to check it again. The next thing that you need to take into account is how you spread out the calibration takes throughout the area that you want to use for your system, in your system. I think we will explain this better on a different video showing the practical way of doing it. Both the pattern and the inclination are important. If we keep the rod still and upward, straight, then we are not providing enough information to the system with regard to the horizontal displacements. That's also an intuitive explanation, but that's the reason why we need to incline, to tilt the rod. Finally, it is also advisable to redefine the grounds. So right after you perform a calibration, it is good to place the 3 markers and follow the ground calibration procedure. That takes exactly 30 seconds, and it is also advisable. If we don't take care of these little things, they add up and they can, result in significantly high errors. These numbers in here are the result of our own tests and experience through years. But if you add a few little errors like this, you may end up with some significant mistake in the final measurements. And then there is this final aspect that can be taken into account during the configuration of the system and the installation. This is just a configuration setting that has to be enabled once in the software, once and for all. It has to do with a phenomenon that we have detected, which is a very rare phenomenon that happens very seldom, mostly when there are few cameras, like 4, and groups of markers that are very close to one another, which is precisely the bike measurement protocols. So in order to explain this, let me just bring up the software here. As it is well known, in order to generate a 3D point, the system needs that at least 2 cameras are seeing its marker. So we need 2 cameras to compute the position in Spain of a marker. In this case, for example, one of these white markers. In this case, bike measurement protocol, all markers are really easy for the system to see. By the way, I'm using the test version, the test 6.11 version, which adds a few more details in the visualization of the bike. We are still working on it, so don't look at the wheels, which are very small. They look like a kid bicycle, but there's nothing to do with that. So don't pay attention to the segments, the size of the wheels, and so on, because the only real thing here are the white dots. The white dots are the markers. All the red dots and the lines are just calculated and estimated by us, but it will help us to see what I want to explain. So in the case of a bike, we place most of the markers on top. So they are very easily seen by the system. As you can see, these 3 markers on the saddle can be seen by all cameras. All cameras, all cameras, all cameras. The same happens with the handlebar markers, the stem marker, but there are 2 markers that are slightly more difficult for the system to see. One is the head tube marker, the other one is the bottom bracket marker. Why? Well, because they are lower and because they are on the side of the bike. If we take the bottom bracket marker, in this case it is placed on the right side, so as you can imagine, it should be seen by cameras 1 and 3. If we go to cameras 1 and 3, here it is. Whenever there's a point here, it means that this camera has seen that marker. The other marker is the head tube marker. It is placed in this case on the left of the bike, as you can see. So we would expect this marker to be seen by cameras 4 and 2, typically 4 and 2. But if we look at cameras 4 and 2, we see that, which is funny enough, camera 4 seems not to be able to see the marker, camera 2 seems not to be able to see the marker, and that's probably because of the handles, which are hiding the marker. So we played a little bit with the bike position until we found a position in which the cameras which were supposed to see the marker cannot see the marker. And well, camera 3, if you look at camera 3, it actually is showing the marker, and that's probably because from the point of view of the camera 3, it could actually see the marker, maybe just about it. So, but what happens with camera 1? Camera 1 is supposed not to see that marker, which is in here. It's supposed not to see, but as you can see, the markers from the right handlebar and that head tube markers are almost in line for this camera. As you can see, they get almost in line. That's what we can see on the view, on the camera view. So the system thinks, okay, there is a spot here, there's a marker. I have another marker, another spot that is seen by camera 3. This one is okay. So there can be 2 spots in line. So let me create a marker using this spot and this spot in here. So the result is a marker, a 3D marker that is roughly in the same position but slightly away. Maybe you think this is too complicated, and of course, how do I prevent this, or what can I do about it? I mean, the system is supposed to know what to do with it. Yes, the system knows what to do with it. We just found a position, playing with it, in which the cameras that are supposed to see a marker cannot see the marker, and yet the system is able to create the 3D position of the marker. So how do we prevent this from happening? It's very simple. We have to tell the system, hey, do not use one spot to create two different markers, which is what's happening, for example, here. One spot to create two different 3D markers. This will radically prevent this from happening. How do I do this? That's very simple. I'll just have to go to configuration. Let me close the recording. I'll go to configuration, options, capture, 2D marker, coincidence, checking. It is usually set to no by default. I just set it to yes for my software installation. Now the system will alert me if this is happening. So whenever I run a new recording, then the bike is detected and analyzed. As soon as the recording finishes, the system will tell me, hey, there is one marker that has been generated with two different 2D spots, two different spots on the 2D views. That's what we can do right now with the release version 6.10. So what we're going to do in the 6.11 version is to radically prevent this from happening by preventing the user to preventing the system to initiate the recording if this is happening. As simple as that. So this is something that, as I say, it just have to be set at the beginning once and for all. This is a rare case, okay, but it can be a source of a relatively high error. If it happens, let's say 1 out of 15 times or 1 out of 20, okay, let's prevent it if possible. Once we activate this option, it will remain enabled for all recordings. We are in this version 6.10, so we're interested in it when we're using the bike measuring protocols. If this window pops up, this alert pops up in the rider measurement, that's not a problem because it's a different scenario. It doesn't affect in that case. So that has to do with the calibration and system preparation. What do I do when preparing a new bike for measurement? Well, basically take into account 2 or 3 different things. The bike positioning is very important, particularly 2 different aspects. The first one is the leveling of the bike. Leveling the bike is important because some measurements are taking the horizontal axis or the vertical axis, like for example ridge, stack, and a few others like these 3 up here, or these 4. Now the way we align the bike with the system is not by using a level and leveling the bike like to the world, so to say. No, we want to level the bike in relation to the floor, because the floor is what we have calibrated. So we want the bike to be parallel to the calibrated floor. To do this is very simple. Just measure the height of the front axle and measure the height of the rear axle. They have to be the same. The distance from this axle to the floor and this one to the floor should be the same. That's the way to ensure the bike is leveled. Second, make sure that the bike is always straight, stable on the support, for the same reason, because we want to be sure that if the bike is placed back to the same position, we want the system to give us the same measurements. But remember that the system is measuring the markers, not the bike itself. So we need the markers to be back on a stable position for the system to be able to give right measurements. The final aspect to take into account is the marker placement. That's pretty obvious. Not just to fix the marker properly so that it doesn't fall, but also to place it on the right position. It's interesting to understand how the system is measuring the different distances. For example, the A reads is measured as the horizontal distance between centers of this marker and the center of this marker. The stack is the difference in height between this marker and this marker. The bottom bracket to saddle BRP, that's the distance between the center of this marker and the surface of the saddle. So the system will be looking at the center of this marker and then subtract a certain distance, a few millimeters, just to find the surface of the saddle. The distance the distance D is the height of saddle BRP over the handlebar. That one is measured as the difference in height between this marker and this marker. Same for the distance E. The distance F is the saddle BRP to the bottom bracket setback. The system will measure the horizontal distance between the center of this marker and the center of this marker, the saddle BRP. The G distance is similar to F, in this case taking into account the saddle tip marker, plus the physical dimension of the marker, or the distance between the center of the marker and the actual tip of the saddle. So the system will be adding a few millimeters. This is an empirical test, by the way, so we know the distance between the center of the marker and the surface on which it is placed, and we add this distance here or subtract this distance here in the case of C. Alright, so the H will be the maximum pedal to saddle BRP distance. That's a simple sum. So we take C and we add the crank length. The I distance is the saddle BRP to stem dark distance. In this case it is from center of marker to center of marker. The same happens with J distance, from center of marker to center of marker. The K distance is the saddle tip to the handlebar stem direct distance. This distance is a direct distance between centers of markers plus the physical dimension of this marker, so that we can actually say we are measuring the tip of the saddle. Handlebar width is pretty straightforward, just direct distance between the handlebar markers. The saddle tilt is just the angle between this marker and this marker that is not depicted here with the horizontal. The N will be the effective pedaling angle, just an angle with horizontal. And the handlebar reach is the horizontal distance between centers of markers, this and this, centers of markers, horizontal distance. If you take into account these ideas when placing the markers, then you'll be sure that the measurements are right. So taking this into account, which is not that complicated, just simple tips, we can ensure that the potential sources of error can be reduced to a minimum, leaving only the two sources of error that we cannot control. One is the maximum accuracy of the system with those cameras, with that resolution at a given distance, which is about 1 millimeter, plus 1 millimeter error in you placing the marker or you measuring with the tape, the measuring tape. That would be the typical error, maximum error that you should expect, instead of a way higher error that can come from different sources. So all these sources can be effectively reduced or completely vanished, so that we can get a very nice and accurate measurement. So I hope this helps. The next step is to test this in practice.